Hello and welcome to Technical Utkranti. And today we are going to see this question in which we find the number of unique paths when we traverse in a matrix from top left to bottom right. The only constraint is that one could only go right or bottom. So we have done 17 questions till now, and this is the 18th question in the arrays. And let's have a detailed look into the question and example solution. This is a 3 cross 3 matrix. This is the initial position. This is the final position. And there could be six unique ways to travel from initial to final point, given that you can only go right or down. So one is right, right, down, down. Another is right, down, right, down, right, down, down, right, right, sorry, down, right, down, right, down, right, and down, right, right. So how are we going to solve it? So one is the combinatorics approach. The way I was illustrating the example, from there only you might have got some understanding of this. So basically, for three rows and three columns, you have 3 minus 1 rights and 3 minus 1 downs. So basically, if there are m cross n matrix, which means m rows are there, so there could be m minus 1 downs and n columns are there, so there could be n minus 1 rights. So these m minus 1 down and n minus 1 rights, what are their different arrangement possible, right? So we know that to arrange n things in different arrangements, there could be n factorial ways. But if some of them are the same things, then we divide them with their factorials. So over here we have m minus 1 plus n minus 1 total number of things, which is m plus n minus 2, and then m minus 1 things are same and n minus 1 are same, which is down and right. So with this factorials we divide and we get the total number of arrangements, and that would be the answer. So let's understand the implementation. Here I have initialized numerator, denominator 1 and denominator 2 as 1. And then I am calculating m plus n minus 2 factorial with this, and m minus 1 factorial with this, and n minus 1 factorial with this. And ultimately I do numerator upon denominator 1 into denominator 2. So this should give me my solution. Okay, let's look at another approach, which is recursive plus dynamic programming approach. So here we'll see a bit of what is dynamic programming and how to use this recursive approach into solving this. All right. So first, let's understand a little bit about recursion. Whenever there is recursion involved, there will be two sets of conditions. One condition would be the terminating condition and another would be the recursive condition. All right. Now, for the time being, we see m and n with initial position and 1 comma 1 with the final position. We start with, so we'll take the example of 3 comma 3. Yeah. So with 3 comma 3, we start off, and for the time being, just ignore these two lines. We'll understand their significance later on. And we see that if m is equal to 1 or n equal to 1, both m and n are 1, it means that we have reached the bottom right of the matrix and we return 1, right? If m is less than 1 or n is less than 1, it means that we have gone out of the matrix and we return 0. These are the two terminating conditions. Recursive conditions are these. So whenever m or n is greater than 1, then we go on to a recursive path. Now let's understand the significance of these two statements. We know that we can either go down or we can go right. All right. So when we do the subtraction, so I'm saying this particular function is computing the number of unique ways, right? I start with m comma n, which is for now 3 comma 3. Now when I am going to go down, so when I go down, then my row will decrease and column would remain same. So when I go down, I go with these arguments and again I feed it over here, right? Because I'm saying this particular function will calculate the number of unique ways given the m comma n. So I say that okay, when I go down, then I have these changed arguments. Please calculate it for me. All right. So 3 comma 3 would become 2 comma 3 over here. It will again come here and 2 comma 3 will sit on stack and m comma n will become 1 comma 3. 1 comma 3 would again come here. The current values of m n would go on stack and this would become 0 comma 3. Now 0 comma 3 signifies that we have from here, we have come over here. All right. So in that case, we will encounter a terminating condition of 0 and we make a return back. When we make a return back, we pop up the last values of m and n from the stack. So m becomes 1 and n is 3. With m equals to 1 and n equal to 3, this particular statement is executed. So for 1 comma 3 minus 1 is called the current values of m comma n goes on to stack and we have m1 and n2 over here. It again comes back over here and as you know for m equal to 1, m minus 1 will be 0 and this terminating condition would be encountered and again the return would happen. So we'll again come back over here and it would be m equal to 1, n equal to 2 and 2 minus 1 would be 1. So m and n would be equal to 1 and this is the condition that would be encountered and we will have a return of 1. So dp of m comma n, which is dp of 1 comma 1 would be 1 and we will be returning the count over here. So whenever return is encountered, whatever values of m comma n in the stack were there, those will be popped up and either this or this function would be executed. So basically there will be execution of all values of uh, all combinations that are possible with down and right, and whenever the control flow is going outside either in this direction or this direction, it would be stopped by this particular recursive condition. And for m equal to 1 and n equal to 1 over here, we'll be adding 1 to the solution. So that would be one unique path. In this way, we will be able to calculate all the unique paths that are there. Now let's understand the significance of these two lines. This is basically when I've done the calculation for m equal to 1 and n equal to 1, I would not have to do it again when let's say I did the computation for this path, right? Now when I'm doing the computation for this path, I already have the solution for 1 comma 1. So after having reached over here, I will just check that whether 1 comma 1 exists, and if it does exist, I will just use that solution instead of computing it. So then I will have the value over here. Then let's say if I have to compute some other value which is dependent on this value, then I will use this value instead of going on computing. This will save me a lot of time. To understand the significance of dynamic programming, I have written the code where we are not using the dynamic programming approach. All right. So here let's do it for 12 comma 12 and see how much time does it take. So for 12 comma 12, you can see it is taking some time. And for when we use dictionary, I mean, when we use dynamic programming, let's see the amount of time it takes. See, it comes then and there. So that fast it is. Let's look at the combinatorics approach. And for m equals to n equals 12, which is 12 called 12 cross 12 matrix, let's see how much time does it take. And it is happening very quickly. So I hope you have understood this recursive approach, the significance of dynamic programming, and the combinatorics approach for the same problem. And I hope you liked this particular problem and solution and the way I explained it. If you did like it, please subscribe and give a like to my video. This will motivate me to come up with more interesting videos and more motivation to make such videos. Thank you. Bye bye. Good night.